Hello everyone who are following my channel and giving me feedbacks on how to continue. Today I will try to do the last year final exam. So let's start from the multiple choice. Thank you. Please like the video lectures, share to your friends who are learning in different Ethiopian universities, who are joining also the freshman courses. Please comment on the video lectures. So the first question from the last year exam is, it says, if the preposition P and Q are given and if P implies Q is a false statement, then the truth value of negation of P and Q by implies negation of P or Q. So to recap from the first chapter of the mathematics for natural science, the first chapter is about logical connectives, and there are 5 logical connectives, and or, which is conjunction, disjunction, implication, and by implication. So for the from this, it's given the implication, the logical connective implication has its own rule. So the compound preposition P implies Q becomes false if and or if the second statement is false and the first statement is true. So we have obtained the truth values of the two simple prepositions from the given compound preposition, given that the compound preposition is false statement. Then let's determine truth value for this compound preposition. So first, let's determine the negation of P and Q. So the conjunction or the logical connective and the compound preposition becomes true if both the simple prepositions are true. Therefore, negation of P is false, and negation of Q and false and false gives a false statement. And the other one is negation of P or Q. And on the logical preposition connective or the which is the same as negation of P and negation of Q. So negation of P is just false, and the negation of Q is true. True and false is just it's also false statement. Therefore, false by implies false. False by implies false becomes what? False by implies false becomes a true. False by implies false gives a true preposition. False by implies false gives a true preposition. Therefore, the choice for the first one is A. The next one is if a set A, B, and C are given, if A is a subset of B union C, then which one of the following is true? So A is a subset of A is a subset of B union C. A is a subset of B union C. Then the first choice, A is a subset of B or A is a subset of C. A is a subset of B or A is a subset of the subset of C. May not be. It can't be. A is a subset of B or B is a subset of it. Cannot be. A intersection B is implicit. A intersection B is implicit. A intersection B is different from implicit. It may be implicit. It may be an implicit because maybe on the case that the elements are subsets of B. Elements are subsets of A intersection C is also different from implicit. It may be an implicit if the elements are subsets of B. and none of the above is not the above is true. Which of the following is false about the set A, bit set 0 and number 1 in the brass? So these are the elements of set A. Then this element is a subset of A. Clearly true. Subset. We should when the elements are coded in the subset, they should be on the braces, on the open braces. And bit set is an element of A. Clearly, bit set is an element A. Bit set is a subset of A. Bit set is a subset of A. Bit set is a subset of A. Clearly true. And 1 is the subset of A. 1 is a subset of A. 1 should be on the it's just put it on the brass, should be deviled when it is a subset. Therefore, the false statement is D. D is a false statement. It's not true. It is not true. The next one is let W be the non-empty subset of the set of positive integers. Then which one is not always true? Which one is not always true? W is a non-empty positive subset of positive integer, set of positive integers. The non-empty subset of a set of positive integers. Then which one is not always true? Now W has a list element. W has a list element. W has a list element. W has a list upper bound. W has a list upper bound. W has a greatest lower bound. W has a greatest lower bound. And the greatest lower bound and the least upper bound, the list elements of W are equal. The greatest lower bound and the least elements of W are equal. So which one is not always true? So W has a list element, clearly true. W has a list upper bound. It may not be true. Sometimes when the set is an infinite set, so has a list upper bound. It may not have a list upper bound. It may not have a list upper bound. W has a greatest lower bound. Clearly, it has a greatest lower bound because a set of positive integers. And the greatest lower bound and least upper bound when the elements should so may not be always true is W has least upper bound. Which one of the following is true? Which one of the following is true? The set of positive integers is closed under subtraction. The set of positive integers is closed under subtraction, which means that the set of positive integers, it means it's not just integers, which is 2 minus 5, which is just minus 3, which is just minus 3, which is not an element of positive integers. So it is not true. The next one, any decimal number is a rational number. Any decimal number may not be a rational number. For instance, x is equal to 22 over 7. Sorry, 22 over 7, which is an irrational number. 22 over 7 is an irrational number, which is an irrational number. And the set of rational numbers is closed under addition. The set of irrational numbers is closed under addition. The set of irrational numbers is closed under addition. And we can locate any irrational numbers on the number line. We can locate any rational numbers on the number line. The set, we can locate any irrational number on the number line. We can locate any rational number on the number line. So which one of the following is true? Which one of the following is true is we can locate any rational number on the number line. Of course, we can represent in between. So if there is any z irrational number, we can locate it between any two rational numbers. We can locate between any two rational numbers, and the set of irrational numbers is closed under addition. So it's may not be closed under addition because the sum of two irrational numbers is rational. The sum of two rational numbers is rational. So the question is the solution for this one is we can locate the set of rational. So it's not true. It's not true. But the last one is true. The other one, if x and y are elements of real numbers are distinct, then one of the following statement is necessarily true. One of the following statement is necessarily true. One of the following statements is necessarily true. X less than y if and only if kx less than or equal to ky for all k greater than or equal to 0. Clearly, x less than y, it has two statements to y proof. X less than y implies kx less than or equal to ky for any k greater than or equal to 0, and the other one is kx less than or equal to ky, kx less than or equal to ky implies x less than y, x less than y, x less than y. You see, it's by implication, if and only if it's the by implication. So does the by implication holds? No. This one holds true because when x is less than y, clearly kx is less than or equal to y. Kx is less than or equal to 1. If k is 0, for instance, k is 0, 0 is less than or equal to 0, clearly. But kx is less than or equal to ky. If kx is less than or equal to ky, cannot imply that x is less than 1. For instance, we can take x and y, which is 1, x and y, 1 is less than 2. We can clearly true, 1 is less than or equal to 2. If we multiply this one by 0, 0 cannot be less than 0. 0 does not imply that 0 is less than 0. Cannot imply 0 is not less than, is less than equal to instead. Or we can take any number, any other number that relates this function. So this statement is not correct. This statement is not correct. So this is not necessarily true. It's not true. If x is irrational, and y is irrational, then x plus y is a rational number. So rational plus irrational gives an irrational number. So this statement is not correct. Rational plus irrational gives an irrational number. If both x and y are rational numbers, then there exists a rational number z such that x is less than z less than y. Clearly, this one is true. Clearly, if both x and y are rational numbers, then we can say that x and y, there may be exist another rational numbers that makes the two proposed, that makes the statement true. So for any two rational numbers, x and y, we can find another rational number. Well, we can find another rational number between x and y. So the state C is the correct solution. For a complex number z, which one of the following is not true for x? So I think this talks about properties of modulus and argument. Modulus of z. Z is equal to the modulus of z. Z is equal to the modulus of the conjugate of z. The modulus of z is equal to the modulus of the conjugate modulus. So which means that if z is x plus iy, if z is equal to, it implies that z is equal to x plus iy, x plus iy, x plus iy, if x is equal to x plus iy, and z conjugate, the conjugate is x minus iy. So what is the modulus of z and z conjugate? The modulus of z and z conjugate, which is clearly, which is z is equal to, the modulus of z is equal to the square root of x square plus y square, which is the same as the modulus of z conjugate. The modulus of z conjugate. The other one is argument of z and z conjugate, and also z inverse of z. So properties of an argument of z, z1 times z2, argument of z1 times z2, which is equal to argument of z1 plus argument of z2. Similarly, argument of z1 over z2, argument of z1 over z2, argument of z1 over z2, which is equal to argument of z1 minus argument of z1 minus argument of z2, argument of z2 minus argument of z2, which is the same as argument of which is the same as argument of z1, argument of z1 times z1 z2 inverse is the same as argument of z1 times z2 inverse, isn't it? So which means that argument of z1 inverse is equal to negative of argument of z, and also argument of z argument of z is equal to negative of argument of z conjugate. So which is the same as argument of z inverse, which is negative of argument of z inverse. Therefore, from those properties, this one is a correct one. So argument of z inverse is equal to argument of z conjugate, clearly true, because argument of z inverse is the same as argument of z, and argument of z inverse is negative of argument of z, and argument of z conjugate is negative of argument of z. Therefore, argument of z inverse and argument of z conjugate are equal, and argument of here is also argument of z and argument of z conjugate are this one. So the choice result not true is D. D is the correct solution. The next one is given z is a complex number, z plus z conjugate, which is equal to z minus 2i. Then what is z? Z minus 2. So it's given z is z plus z modulus, which is equal to 6 minus 2i, 6 minus 2i, 6 minus 2i. Now let's take that z is equal to x plus iy. Z is equal to, let's say, x plus iy. Let's take z is equal to x plus iy. Let's take x plus iy. Then the modulus of z is the square root of x squared plus y squared, x squared plus y squared, x squared plus y squared is equal plus z is equal to, z is the same as x plus i, x plus iy, x plus iy is equal to 6 minus 2i, x minus 6 minus 2i. So clearly we can see that this one is the real part is this one, and this one is the imaginary part. This one is the imaginary part. Therefore, equating these two terms, you will get, the square root of x squared plus y squared, x squared plus y squared, x squared plus y squared plus x is equal to 6, and iy is equal to minus I times 2, So cancelling those I terms, y gives cancelling those terms, y gives 2 minus 2. Y implies y is equal to minus 2. Now substituting this one, y is equal to minus 2 on this equation. We will get the square root of x squared plus 4. X squared plus 4 is equal to plus x is equal to 6. So which is the same as x squared plus 4, the square root of is equal to 6 minus x. So which implies that which directs that x squared squaring both sides, x squared plus 4 is equal to 6 minus x, the whole square, 6 minus x the whole square. So what's the x squared plus 4? Now square the 1, you will get 36 minus 12x plus plus x square plus x square. You get this one. So x square will be cancelled by this x square. So what's left? What's left is 12x. 12x is equal to 36 minus 4, which is 32. So x is equal to 32 over 12. 32 over 12, which is the same as cancelling by 4, which is 8, cancelling by 4, which is 3. So x is equal to 8 over 3. Therefore, z is equal to 8 over 3 minus 2i. Z is equal to 8 over 3 minus 2i. Z is equal to 8 minus, from the alternative, 4 minus 2i, 8 over 3 minus 2i, 6 plus 2i minus 8 over 3 2i, which is the exact solution is 8b is the correct solution. B is the correct solution. The next one is which one of the following relation is not a function? Which one of the following relation is not a function? X comma x squared, where x is a real number, which is y, which is f of x. We can say f of x is equal to x squared is clearly a function. This is a function. X comma y, x is a triangle, and y is area of triangle, which is g of x. We can say g of x, which is equal to area of a triangle, which is 1 over 2. Area of a triangle, which is exactly maps to a unique element. So for a given triangle, the area of the triangle will be mapped to the x maps to a single area of triangle. So which is also a function, x comma y, an element of a cos a. X is a prime factor of y. Where a is 2, 6, 7, 11. 2, 6, 7. So x is a prime factor of y. Means the prime factors are just 1, 3, 5, 7, something just like this. So when we are ordering x to y, we cannot find just similar to this one. So 2, 6, 7, and 11, using these elements, we can form a function. So which is the correct answer. The other one, consider the polynomial function p defined by p of x a naught plus a1, which is a polynomial function of degree n, given polynomial function of degree n, where an is different from 0 and ai's are real numbers. And now, if x is equal to a plus bi, where b is different from 0, is the root of the polynomial function p, then which one of the following is not necessarily true? Now, so the polynomial function p has given one root, a plus bi. So by using the conjugate root theorem, the conjugate of this complex number is also the root of this polynomial function. So we have obtained two roots of this function. So y is equal to a minus ib is a root. Clearly, the conjugate of this polynomial function is a root. P has at most n minus 2 real roots. Which means since we have the polynomial function of degree n, will have at most n roots. So we get two of these roots. The two roots are complex numbers. So for a given polynomial function of degree n, may have at most n roots. So two of them are complex numbers. So we have at most n minus 2 real roots. The p has at most n roots. It can't be, because the two complex numbers are the roots of this polynomial function, so that p does not have n roots and none of that. So which this one may not be. This one is not a true statement. Okay, on the next section we will see the part 2, which is blank space questions, short answers. So we will see that one. Please follow my channel. I will come soon with the next video. Please subscribe my